Hello. In this video, we're going to talk about single supply operation of op-amps. We are used to seeing most op-amps in the preceding videos as having two supplies. Of course, the power supplies are distinct from the signal path. The signal path will correspond to the two inputs, the inverting and non-inverting inputs, and the output. But then the op-amp, in order to provide amplification, needs to draw that energy from somewhere, and it draws it from the power supplies, which are sometimes left out when we draw the circuit schematics, but sometimes they're included. And if so, there are going to be these two pins sticking out the top and the bottom of the op-amp. And typically they're going to be labeled V plus and V minus if they are dual supplies. Sometimes there are alternative names as VCC and VEE, VDD and VSS, and not always, but most of the time they're going to be symmetrical. So for example, for the 741, if you look at the EC table, you can see that it's being characterized and tested at plus minus 15 volts. And there are different values that you will encounter. Plus minus 15 is very common, plus minus 12, plus minus 10. In low power applications, you can even get as low as plus minus 5 and so forth. But the idea is that they're going to be symmetrical, and so our signals are typically going to be centered around 0 volts. So the reference voltage that those supplies are being referenced to is the ground level. Oftentimes, you find op-amps that are meant to be operated from a single supply. And when they're meant to be operated that way, they're typically indicated as the second drawing here. The signal path is still the same, still a differential input and the output. But instead of having two supplies, you will see it has a positive supply and then a ground. Now, the idea behind these op-amps is that they are going to need to be biased somehow. Because if you were just, if you were trying to input some kind of input signal that was centered around 0 and was able to take on positive and negative values, you will see that the negative values will not be amplified by the op-amp, but you will basically be running into saturation issues because you will be running into your negative supply effectively, which is in this case ground. And so there's going to be an extra step involved, the step of biasing the input signal or biasing the op-amp so that it's operating at a reference voltage that is higher than ground. And that is so that your input and output signals will stay far away enough from effectively the two supplies, but the lower supply in this case. Because it requires additional biasing circuitry, the design of single supply op-amps is going to be just a little bit more cumbersome. It also has some additional drawbacks, and is that in some cases, if you are providing the bias voltage from the same supply as you're powering your op-amp, you're going to run into issues of power supply rejection ratio, because basically any variation in your power supply is going to affect directly your bias voltage and things like that. Sometimes they can be also more prone to oscillations, etc. And so there's nothing that we could say is ideal about single supply operation. So why do we bother to sometimes have single supply operation? And the answer is that sometimes in particular applications, we don't have more than a single supply available. You can think of, for example, in some electronic equipment where you have a single power supply perhaps, or automotive applications where you have a single power supply, typically 12 volts, etc. And so in some cases, the need will arise to use the op-amps in this configuration. Normally, there are specific op-amps that are going to be labeled as single supply op-amps, and it's better to use those because they're typically the design has been optimized for use in these configurations. And then as we're using those op-amps in these applications, it's always a good idea to take a look at the datasheet to see if there are any particular application notes or suggestions for particular connections to avoid all these additional issues. The other thing that we perhaps want to mention is that because we're going to need to bias our op-amp, so essentially what we're going to be doing is raising the reference voltage to some arbitrary voltage, but more often than not, we like to keep the reference voltage centered between the two rails, and so typically it's going to be centered between the supply and ground in this case. But because we have to add that bias, sometimes that bias voltage, we don't want it to interfere with our input signal. Let's say our input signal is centered around 0 volts, but yet we have to run it through our operational amplifier, which has a reference voltage that's set at, I don't know, let's imagine Vs is 10 volts, so it's set at 5 volts, halfway between 10 and ground. We don't want our input signal DC level of 0 to interfere with the bias voltage of our op-amp, and so we're going to need to use coupling capacitors, much like what you will do in a common emitter amplifier and so forth, coupling capacitors to feed the signal into the circuit without altering that bias point. And then if you want to avoid the offset at the output, you will use another coupling capacitor to basically extract your output signal and eliminate the offset voltage introduced by the op-amp bias circuit. And so the type of amplifiers that you will design with this single supply are typically AC coupled amplifiers, whereas most of the amplifiers we've been seeing, or the applications for the dual supply op-amps, have been DC coupled amplifiers. So a DC coupled amplifier, of course, is one that amplifies all the way to DC. So we know that all op-amps have high frequency limitations, and so the gain will roll off at high frequencies due to the internal limitations of the op-amp, internal capacitances of the transistors that comprise the op-amp. But in a DC coupled amplifier, we expect that the magnitude of the gain will extend all the way to DC, and then at high frequencies it will start rolling off. Whereas in an AC coupled amplifier, basically you are eliminating the DC component, or filtering out the DC component, and then you are providing a constant gain over some midband region, and then of course you still have the roll-off at high frequencies. And so since we need to have that extra biasing voltage in the single supply op-amps, typically they're going to be AC coupled, where we want to filter out any DC offsets from our input signals. So let's take a look at an example of how we will set up a single supply op-amp. So let's imagine we have just a simple application. Let's use the inverting amplifier as our application. First thing, if we have a single supply, and I'm going to specify that by tying one of my terminals to ground. Now, normally the negative terminal, it's drawn next to the negative input terminal, but that doesn't have to always be the case. It's just a convention. And so here is going to be my positive voltage. And then I'm going to run it. Let's imagine this is my DC supply. I'm going to call it Vs. And then I'm going to run it through a voltage divider of 2 resistors, which I will label R and R. And so what I am doing effectively with this is I'm setting my positive input terminal of the op-amp, which in an inverting amplifier I will normally tie to ground. I'm instead tying it to the midpoint between Vs and ground. So if my supply is 10 volts, I'm tying that, I'm setting that reference level at 5 volts. Now I'm using a voltage divider. A voltage divider is not the only possibility or how to set that voltage, and in fact it's one of the least robust, if you will. Because any variation in supply voltage will, for one thing, shift your reference voltage, which is never a good idea. But there are other possible ways of setting up that voltage. A Zener diode can be used to set up a reference voltage. You can also use a voltage regulator, even though it will add complexity to your circuit. But if you really needed to have a very stable voltage, you could go that route, etc. So once I have that reference point set there, then I can go ahead and connect my inverting amplifier. Same connections as I will normally have. This is my output voltage, and these are my resistors, which I can label RI and RF. Now, normally, this could be it, except if I have an input signal now, which let's say is centered around 0 volts, that's going to interfere with my my reference voltage. And so since I don't want anything to interfere with the biasing of my op-amp here, I'm typically going to add at least an input coupling capacitor so that the DC value of my input signal will not interfere with the reference voltage of my op-amp. And so I will feed my input signal there. And then in this case, my output voltage is going to have a DC offset associated with it. I'm going to call this V out. It's going to have a DC offset. If I wanted to eliminate it to get an output that is centered around 0, I can do the same trick and just run it through an output capacitor, and then I could get my, I'm going to call this V out prime, since it's the output of the op-amp, and V out will be the output of my overall circuit once it's filtered. So let's take a look at how the different portions of this circuit operate. So there's a DC component to my signals and an AC component. The DC component is set because of the bias of my op-amp, and then the AC is, just comes from the AC signal that I'm feeding into the amplifier and that I'm amplifying effectively. So I can basically look at my DC equivalent circuit and my AC equivalent circuit for this particular amplifier. I'm going to draw my DC equivalent circuit first. And in my DC equivalent circuit, my capacitors act as open circuits. My AC sources are turned off, and so the only source that is remaining here will be the supply Vs, which is a DC source. And so I will have essentially the following. This is grounded. I have my RF resistor in this case. Now notice that I'm not going to draw Rin because it's going into an open circuit, so essentially no current is flowing through that branch. And then here I have my Vs, R and R. And by looking at this DC equivalent circuit, I can label my output voltage as capital V out for the DC component of V out. And this is going to be equal to, so V out, notice that this has the configuration of a voltage follower where the input signal, because of the voltage divider at the input, is basically half of Vs. And so my V out is going to be equal to Vs divided by 2. That's my DC component. And then I will have my AC equivalent circuit, which I can draw right underneath. In which I am going to turn off any DC sources. Now, I'm still going to assume my op-amp is powered up, but I'm not going to apply my DC source to my input path, to my signal path. And so I will have in here, essentially, if I'm not applying my Vs DC source to my input signal, essentially what I have is two resistors of value R connected in parallel, both going to an AC ground. So I can just replace that with a resistor of value R halves, which is the parallel combination, the equivalent resistance of the parallel combination of R and R. And let's assume that for frequencies of interest, my capacitors act as short circuits. So this is Ri, this is Rf, and this is my Vin. And I'll call this my little VO for the AC component. And this, of course, is just a regular inverting amplifier. So little VO, or the AC value of VO, is going to be negative Rf over Ri times Vin. So my overall voltage at this point is going to be equal to the sum of the DC component plus the AC component. So this is capital VO plus little VO. And that's equal to Vs divided by 2 plus, or minus, in this case, Rf over Ri times Vin. And then notice, of course, my my V out at the end, or after the C out capacitor, is just simply equal to the AC component, so negative Rf over Ri times Vin. So if I were to represent graphically what's happening here, right, is that I have my input signal as a function of time, Vin. And let's imagine I draw it in blue, and I have just a sine wave centered around 0. Then what I will get at my output before the capacitor is something that is centered around Vs divided by 2. And it's inverting, so inverted with respect to the input, and potentially with some gain. And let me try to do it a little bit better so it actually looks like it is inverted. There we go. And then, of course, after you go past the coupling capacitor C out, then your DC offset will disappear and your output signal will be centered around 0 again. Now, an important question will be, well, how do we select these coupling capacitors, C in and C out? And the answer is that C in and C out both form high-pass filters with the resistances attached between their terminals. And so normally we are going to have some frequency of interest that we are going to want to amplify, or a range of frequencies, but in any case some minimum value of input frequency that we still want to amplify. And we want the cutoff frequency for our high-pass filter formed by the coupling capacitors. We want it to be lower than the smallest frequency of interest, so that we don't end up filtering any frequency of interest. And so I can draw this over here. For example, in the case of, let me just say, coupling capacitors. And so in the case of C in, we will have, this is C in, this is the input resistance to my circuit, and this is the high-pass filter that gets formed. This is my input signal that is fed through C in, and then I guess we can call this V in prime. This will be what actually gets fed to the amplifier after it goes past the capacitor. And this is the input resistance of the amplifier, which in this case is just Ri. If you look at the AC equivalent circuit, because for signal purposes we're just thinking about the AC equivalent circuit, because remember this is an AC coupled amplifier now. And so I have my input resistance basically being Rin, which is connected to a virtual ground. So this will be just Rin. And so I will want my my cutoff frequency, H, or I'm just going to call it Fci, will be equal to 1 over 2 pi Ci Ri. And again, I want this frequency to be lower than my smallest frequency of interest, because remember, for a high-pass filter, my magnitude response is going to look something like this. And so this is going to be my cutoff frequency, essentially. Okay, and I don't want to attenuate any of those frequencies. In the case of the output capacitor, is a similar thing. I have, this will be my C out, and the equivalent resistance will be the equivalent resistance in between the terminals of that capacitor. So this is essentially my V out prime coming out of the amplifier, and this is my V out after it's been, after the DC offset has been removed. And the resistor will be the equivalent resistor connected to the output of my capacitor, which I haven't connected a load here, but in essence it will be the load of the circuit, because if you look back at the amplifier, you could say, well, I have RF connected there, but notice that RF is in parallel with the output resistance of the amplifier, which is going to be typically very small, close to zero. And therefore, if you have a load connected at this point, I'm going to go ahead and connect it now. So imagine this is my RL. That load will appear here as well. And that will be the one that will determine, since it's going to be much larger than the output resistance of the amplifier, that's typically the one that's going to determine that cutoff frequency, cutoff frequency output, which will be 1 over 2 pi C out RL. So that's it. It's not very different from designing just the standard op-amp circuits, but as you can see, it does require that additional step of setting up the biasing network, and then of making sure that you're adding the coupling capacitors so that your signal levels won't interfere with your bias point. Thank you.